Hey, before we get started, can I please get confirmation that you guys can hear me clearly? You guys can see me and then see my screen as well. Was that a yes before I could ask the question? Can you guys see my screen? Is my screen visible? Okay, cool. Those on YouTube, I hope you guys can hear me clearly as well. Okay, let's be thinking. Okay, so we're going to just go through some charge stuff from last week, just to revise it. Okay, a couple of you guys wanted to go through it again, so let's do that, right? So, firstly, we can talk about charge one more time. Okay, so we remember we said a charge is basically an excess amount of protons and excess amount of electrons. So excess electrons would mean there are excess amount of negative charges. Excess protons would mean that there are extra amount of positive charges. Okay, we went through this formula. N is equal to charge over electrons charge. N is equal to Q over QE. Okay, and we went through a formula. Okay, let me just reshare my screen. Huh? Hello. Sorry. I saw the chat late. Okay, you guys should be able to hear me now. Sorry. Technical issues today. Okay. So I was so eloquently explaining that this here is the number of electrons, while this is the total charge, and this is the charge of a single electron. So we're taking the total charge, dividing it by the charge of a single electron. Okay, there's multiple electrons that create that charge. When you divide it by the single charge of an electron, you get the total number of electrons. So I was just saying, okay, you go to the shop and you spend 5,000 Rand on chocolates. Who knows why? Okay, just say you spend 5,000 Rand on chocolates. If you want to know how many chocolates you bought, you can divide that number by the price of a single chocolate, and that's going to give you the amount of chocolates you bought. So it's a very dumb explanation, but it's kind of a similar thing, right? And that tells, okay, that's a very bad number. Let's just use 20, I guess. Okay, that tells us that you bought 250 chocolates. Okay, so again, like I said, it's a silly explanation, but it's a similar concept, right? To where you have total charge divided by charge of single electron gives us number of electrons, or like here, the total charge is equal to number of electrons times charge of single electron. Okay, that also makes sense. Okay, and then in this case here, right, they ask us how many excess electrons make a charge, and we need to note that this is the formula that we use. electrons, this is the formula that we use with electrons in, okay? N is equal to Q over QE. We need the charge of that specific charge divided by the charge of a single electron. That's going to give us the total number of electrons in a specific charge, okay? So that's what we went through, right? Then we did an example, okay? Okay, before we continue, let's look at this quantization of charge. Okay, just 1 second. Let me open my... Okay, we went through quantization of charge, which is basically the formula we just went through. Let's do some examples. So they say the charge on a single electron is equal to negative 1,6 times 10 to the negative 19. Electrostatics. Oh, this is grade 10, sharks. Okay, the principle of charge quantization, all charges in the universe consist of an integer multiple of the charge of an electron. We are looking for, okay, here we go. Okay, perfect. Okay, so the charge is Q, number of electrons is N, and the charge of a single electron is QE, that's negative 1.6. Okay, we've been through that 500 times. Let's look at this. Calculate the number of electrons gained or lost by a positive 4,5 nanocoulomb charge. Okay, so remember we learned these little guys. Okay, I'll put the printed table. I'll replace this writing with a printed table. But yeah, we have milli, micro, nano, and pico. We always want to convert to coulombs. And if it's not given in coulombs, if it's given in one of these four, we convert it to coulombs by multiplying it by each respective scientific notation thing, right? So in this case, right, what you always want to do, if you want to calculate the number of excess electrons or excess protons or electrons gained or electrons lost, because those are similar concepts, right? Electrons gain is going to lead to excess electrons. Okay. Electrons lost is going to lead to excess protons. So if they use those terms, don't be confused by those as well. When they say excess protons, that just means electrons lost as well. So let's just say in A, right, 4,5 nanocoulomb charge, okay? So this is actually the charge. So if I want to calculate the number of electrons, I'm going to say N is equal to Q over QE. I'm going to substitute this value as 4,5. It's nano, so I times it by 10 to the negative 9, divided by the charge of a single electron. Now, because it's a positive charge, okay, someone tell me in chat, right? Since it's a positive charge, does that mean it lost electrons or did it gain electrons? If it's a positive charge, did it lose electrons or did it gain electrons? Like those people that put question marks after the answer, like lost, maybe, maybe not. Okay, correct, lost, right? It lost electrons because that's why it became positively charged, right? It's a very simple understanding of if you have, okay, this is what we call neutral. Okay, in a neutral atom, positive, in this case, we have 5 positive charges and 5 negative charges. Okay, now if we remove, okay, in this case, what are we doing? If we remove electrons, okay, if we remove electrons, we can see now that, let's just say here, we have what we call a positive 2 coulomb charge. Why positive 2? Because we have 2 excess protons. So it's charged positively by a magnitude of 2. I think maybe we can say that. It's charged positively by a magnitude of 2. So in that case, we can understand, oh, okay, the reason we have excess amount of protons is because we actually lose electrons. Okay, we only in this section, we work with losing and gaining electrons. If we have to lose protons, we can there see that, okay, we have excess electrons. Why? Because, okay, no, that's actually not true. Sorry, let's take this back. Generally, what happens is we gain electrons, maybe from the outside orbital. These two extra electrons just shift in there, and we can see, oh, okay, it's not neutral anymore. We have an extra amount of electrons, and that would be a negatively charged. Okay, that's just a simple explanation of what could possibly happen. Can't see screen or hear anything. I think you might need to join. I think you might need to join the audio and then just refresh your Zoom or something to see the screen. Okay, so yes, in that case, we understand that either way, we understand that, okay, this here, because it's positive, it actually lost electrons. So remember I said that when the charge is positive, you will substitute a positive QE. So I'm going to substitute positive 1,6 times 10 to the negative 19. Okay, so you'll see in your formula sheet, it's negative, but when the charge is positive, substitute a positive, and that gives you an answer of, when you divide 2,81 times 10 to the 10. Electrons lost. Okay, so you see, number of electrons. When you have a number of something, you can't get a negative answer. Okay, it's like number of potatoes. You can't get -5 amount of potatoes. So this is a similar concept, number of electrons. You cannot get a negative amount of electrons. So that's why you will always match this sign to the sign of your charge. So let's look at B. Okay, in B's example, okay, in B's example, they want us to calculate the excess amount of electrons or protons, or alternatively, did it lose electrons or gain electrons? So again, because it's negative, right? Okay, so actually, sorry, they wanted us to calculate the number of electrons gained. So yeah, there we calculated it, right? Number of electrons gained or lost. Here we calculated number of lost. So now we need to calculate the number of electrons gained or lost for number B. So tell me, electron B, the charge at B is negative. Does that mean that it gained or lost electrons? Correct. It had to have gained electrons, okay, to have those extra negative charges. Okay, it had to have gained electrons. So in that particular case, what we do is N is equal to Q over QE, which is then equal to 9. This is, I think that's microcoulombs. I think it's 10 to the -6. Divided by, but it's a negative, sorry. So I use negative 9 times 10 to the -6. And when my charge is negative, I use the negative 1,6 times 10 to the -19. And here I get that the number of electrons, because that's what N is, by the way, I'm just substituting N with number of electrons. I get an answer of 5,63 times 10 to the 13. This is electrons gained. Okay, this N doesn't have a unit, okay, because it's electrons. It's number of electrons, sorry. Again, it's like number of bananas, number of apples that you buy from the shop. Similarly, this is number of electrons. It's a specific amount of electrons, okay? It's obviously a high amount of electrons. Okay, so I hope that makes sense. That's this formula, okay? Now we can discuss this one more time. Let me just see this one. Asks the due charge on each, amount of charge transferred, and number of electrons transferred. So let's do a new question, okay? And then we can discuss all the concepts that we discussed last week as well. And then we can try and move on to electricity as well. Okay, we can start it at least. So question number 8. Okay. So two spheres S and T on insulated stands carry charges of -7 times 10 to the -9 coulombs and 5 times +5 times 10 to the -9 coulombs respectively, shown below. So they're given in coulombs. Perfect. We don't need to convert, right? This could also be seen as, because it's times 10 to the negative 9, this could also be seen as negative 7 nanocoulombs. And this could also be seen as positive 5 nanocoulombs, right? But we always want to use coulombs in our formula. But if they had given it to you like that, please note that you'd have to convert it to coulombs. So number 8.1, which sphere S or T has excess of electrons? Somebody asked answer. Which sphere S or T has an excess of electrons? Correct. Okay, S. The reason is because it's a negative charge. So therefore it has a negative amount of electrons. Okay, so our answer is S. Calculate the number of excess electrons in excess. Okay, we've done a question like this. Let's answer it below. 8.2. We're going to calculate the number of electrons. The only formula we know with number of electrons is N is equal to Q over QE, where Q is going to be the charge. So I think it's negative 7 times 10 to the negative 9. Okay, negative 7 times 10 to the negative 9 divided by QE is, I have to use the negative QE because my charge is negative, negative 1,6 times 10 to the negative 19. Okay, I'm going to do this calculation. So negative 7 times 10 to the negative 9 divided by negative 1.6 times 10 to the negative 19. I get an answer of the number of electrons as 4,375 times 10 to the positive 10. Again, there's no unit. It's just electrons. Okay, cool. Moving on, the spheres are now allowed to touch each other and are then separated. Okay, so S and T come close together, they touch each other, and then they are separated. Okay, so remember what happens when two charges touch one another. Okay, electrons will be transferred. Okay, electrons will be transferred. Okay, and after they are removed from contact, okay, when they are separated again, basically, they will have the same charge. Okay, remember that. So they have different charges. They are brought to touch each other. Thereafter, they are separated. And when they are separated, they have the same charge. So let's answer the question. 8.3. In which direction will electrons flow while spheres S and T are in contact? Okay, write down only from S to T or T to S. Yes, tell me, S to T or T to S? Okay, people in YouTube as well, don't be shy to answer the questions. I think the YouTube is slightly delayed, but I don't think it makes a difference because I see your question, I see your answer delayed, you see me delayed, so it works out. Okay, everyone's saying S to T. Anyone says T to S? Okay, no one says T to S because it's the incorrect answer. S to T is indeed correct. Why is S to T correct? Because remember this, electrons, okay, always move from, not from negative to positive, from the more negative, okay, to less. From more negative to less negative, always. So that's why it's going to move from S to T, because negative 7 is definitely more negative than positive 5. So the correct answer is from S to T. Okay, calculate the new charge. So we're looking for the keyword new charge. Calculate the new charge on each sphere after separation. New charge formula is set. So you need to understand, you need to memorize the terminology, memorize the keywords. Okay, let's go back to last week's work. Here's it here, new charge. Q new. It has, even the formula has it in it, Q new. So new charge after contact is Q1 plus Q2 over 2. New charge after contact is Q1 plus Q2 over 2, which is Q new. Q1 is -7 times 10 to the -9 coulombs. Q2 is 5 times 10 to the -9. So I'm going to say -7 times 10 to the -9 plus -5, +5, I think. +5 times 10 to the -9 divided by 2. So the Q new, okay, when I do this calculation, I believe is -1 times 10 to the -9 coulombs. So after they are brought into contact and then separated, remember, charge electrons are being transferred from the more negative to the less negative while it's in contact. They're then separated. They have the same charge, and that charge, each one has -1 times 10 to the -9. They went a bit easier on you guys, so I'm going to add more questions. Let's look at 3 more questions. I don't know. Okay, let's do these questions. Okay, so 8.5 says calculate the charge transferred. Okay, so 8.4 said calculate the new charge on each sphere after separation. 8.5 said calculate the charge transferred. So let's go back to our formula. We have a formula for charge transferred. It's known as delta Q. Delta Q is equal to Q final minus Q initial. Q final is the new charge on each. Q initial is the original charge before contact. Okay, so charge transferred, we're going to use, again, the vocabulary is key. Charge transferred. Which is basically Q delta Q. Delta Q means change in Q. Q final minus Q initial. So Q final we know is definitely -1 times 10 to the -9 minus Q initial. Now, Q initial is before they were made to touch. We have 2 options, right? We have 2 initials. Which one should I choose? Should I choose S's initial or should I choose T's initial? Okay, some people are saying S. Anyone, I can choose any of them. Okay, I can choose because they're both initials. Okay, and I'll show you the difference. So I'm going to choose -7. -7 times 10 to the -9. And I'm going to get an answer of 6 times 10 to the -9 coulombs as my delta Q. Let's see if I chose the other one. Delta Q is equal to Q final minus Q initial. This is equal to 1 times 10 to the -9 minus, I'm going to choose +5. Wait, is that right? Sorry, it's -1. Minus 5 times 10 to the -9. When I do this calculation, I get delta Q as -6 times 10 to the -9. So the change in charge is -6 for the more positive. Remember, 5 was the more positive. Sorry, we call it the less negative. Call him less negative. So if I chose the less negative initial, I'm going to get a negative answer. And I'll explain why in a bit. But when I chose frozen. When I chose the more negative, I got a positive answer. Why is that so? Okay, so basically, see, this guy is negative and this guy is positive. Okay, so this one is the more negative and this one is the less negative. So remember what happens is S actually donates to T. Now, because S donates to T, S is losing electrons. S loses electrons, so it becomes more positively charged S. Not positively charged, it becomes more positive. Just going to do it like that, more positively charged. Since it becomes more positively charged, that results in a positive delta Q. Why? Again, because it is losing electrons. When you lose electrons, it's like you're becoming more positive. Okay, we're not multiplying though, Blake. We are not multiplying. We are just subtracting. So we cannot use that logic per se. We are subtracting. It's a minus and a plus. Okay, makes a more minus, but this is the logic behind it. So because S is losing electrons, it's becoming more positively charged. Therefore, it has a positive delta Q. It's like losing, it's like giving its electrons to the other one. So because it's giving it electrons, it's becoming more positively charged. T on the other hand, okay, he's just sitting, chilling. He's more positive normally, but he's actually gaining electrons now. Because he was originally the less negative one, he's now gaining electrons. He is becoming more negatively charged. Because he is becoming more negatively charged, okay, he has a negative change in charge, a negative delta Q. What can we say? Remember, this is for the more negative guy. It's true for the more negative one. And this is for the that is deplorable. I guess this is for the less negative one. This is true for the less negative one. So if your initial, you choose the less negative one, you're going to get a negative delta Q. If you're going to choose the more negative one, you're going to get a positive delta Q. Okay, and it doesn't matter. You could use both. Okay, so again, I have +6 and I have -6. Let's look at the next question, which requires us to use our answer from 8.5. Now, 8.6 says how many electrons were transferred. So again, now we're dealing with electrons transferred, keywords. Firstly, the only electron formula we know is N is equal to Q over QE. So that's most likely the one we're going to use. Let's go back to our notes. Oh, we actually talked about it. We said where electrons transferred is the key word. Okay, this is the formula we use because it contains the electrons transferred. Remember this, very importantly, I mentioned that these need to match. Okay, so I'm going to show you a simple explanation of that. Q is equal to, okay, I'm going to rearrange it and I'm going to say N is equal to Q over QE, where I'm calculating the electrons. Now, if I am calculating, if I want to know the number of electrons of charge, it's a random charge of charge A, this is too fat, okay, of charge A, right? I need to use the charge of A as well. Divided by QE, the constant. Okay, if I want to know the number of electrons of charge B, I need to use the charge beat. Sounds obvious, but believe me, it's not. So therefore, if I want to know the number of electrons transferred, okay, what do I need to know? What kind of charge do I need to know? I need to know the charge transferred. It needs to match. They need to match. So again, if I want to know number of electrons transferred, I need to utilize the charge transferred and divide that by QE. If I want to know the number of electrons on top of the Eiffel Tower, I need to know the charge on top of the Eiffel Tower, whatever. But these need to match. Again, if I need to know the number of electrons at B, I need to utilize the charge at B, and vice versa. Meaning, if I want to know the charge transferred, I need to know the number of electrons transferred if I want to utilize this formula. Okay, so please keep that in mind. This is very important. Okay, so in this case, they want to know the charge transferred, sorry, electrons transferred. So in order to get electrons transferred, I need to know the charge transferred. Okay, so now I'm going to use N is equal to Q over QE. In fact, it's going to be, because it's number of electrons transferred, I'm going to be using, any questions? No. Charge transferred divided by QE. So it's basically going to be N N is equal to delta Q, which is charge transferred. This is one and the same thing. Divided by QE, which is a constant. Okay, I hope that is making sense. So in this case, delta Q, if I choose the positive one, then my QE needs to be positive as well. If I choose the negative one, then my QE needs to be the negative. Because N is always going to be a positive value, and then negative times the negative gives me a positive, and a positive divided by a positive gives me a positive. Okay, so both of these are all going to give me the same answer of the number of electrons transferred. It's going to be an answer of, if I just have to estimate and definitely just use my brain and to the calculation without the calculator, I would assume that the answer is going to be somewhere close to 3,75 times 10 to the 10. Okay, and I can say electrons transferred. Okay, hope that makes sense. If it doesn't, too bad, so sad. No, I'm joking. Okay, if it doesn't, right, if you're still a bit confused, I would recommend rewatching the video, right, when it gets uploaded, just to try and get a better understanding. If you still don't understand, then contact me, okay? But yes, that is basically all you guys are responsible to know for electrostatics. Okay, it's not bad. And trust me, if you master your basics now, it's going to make grade 11 a lot easier and grade 12 a lot easier as well. If you truly understand, I would say that this is very important for grade, like if you're going to continue to take physics, like your basics are, if you know your basics extremely well, if you understand all the concepts extremely well, you will be fine in grade 11 and 12. Okay, to test your basics very well, I have a question that I want you guys to do for homework that we will go through next week. If I forget, please remind me, but please do this for homework on your own time. And yeah, this is a test of how well you understand the section. Okay, very nice. Let's just maybe write the formulas here quickly. So new charge this is Q new is equal to Q1 plus Q2 over 2. Charge transferred, we said, was delta Q is equal to Q final minus Q initial. Okay, see how they link also, right? Like when they ask, this is actually delta Q because we're calculating charge transfer, right? So when they ask Q new, okay, we get Q new. And how do we use Q new? Here. Okay, also, by the way, this could be also written as Q new. Actually, I prefer that. I don't know why I use Q final. Q new minus Q old. That's a nice one because it's like it relates them more. Q new minus Q old. Okay, in that case, do you see how they like link, right? So what I mean is, once you get Q new, you can then get delta Q. Once you get delta Q, you can then get electrons transferred. Okay, you need to understand properly. That's the wrong one. Talking about Q new, which is the same as Q final, but it's just the same wording is better. So once you get the Q new, you can get the delta Q. Once you get delta Q, you can get electrons transferred. Okay, so you need to note how they link. That's extremely important. If you understand that, you understand the section. All right, let's move on. Okay, let's take a 1 minute breather, even though we don't have. Okay, actually, let me just go to the bathroom. So sorry. So like 2 minutes, 2.5 minutes, 2 minutes, 46 seconds. And then when we come back, you guys can take a breather, go jump in the sky, I don't know, whatever. And then we'll be back shortly and we'll continue with electricity. Hey, good evening. I'm back. Sorry, I know I see someone says 2 minutes have passed. I didn't know that. I was in the bathroom, so I couldn't tell. I apologize. But anyway, let's get cracking. Okay, so electricity, all right. Let us start off with some theory as we do. Everything's fine, right? I think you guys can hear me and everything's cool. Perfect. So electricity. Electricity is the process of giving energy to a charge and then using that energy to do work, right? So the application of electricity is part of every single aspect of our lives at this point. Okay, most things that we do involve electricity. Okay, when there is load shedding, we get bored and we don't know how to do it. We don't know how to do it our lives. Even if for example, some of us have UPSs for the Wi-Fi. If we don't know what to do without the Wi-Fi. If our phones are dead, we don't know what to do with our phones. Everything involves some sort of electricity. Okay, so yes, the most basic circuit is made of a power source and a load and conducting wires carrying the charge around the circuit. So let's look at this basic diagram where it says the power source gives electrical energy to the charge. Okay, so electrical energy, electricity in the form of energy is created by a power source such as a battery. Okay, and it gives the electrical energy to a charge. Okay, the charge travels along the conducting wire. Okay, it travels all the way to the load. The load is the device that uses that energy. Okay, the load is the device that uses that energy of a charge. Okay, so the charge travels to the load is what needs the energy. For example, if your house plug, if a plug in your house is charging your phone. Okay, a simple, also in electricity we do light bulbs. Okay, we use light bulbs, we use resistors. Okay, so for example, a simple circuit with a light bulb, we have a power source, the load is the light bulb, the power source provides electrical energy to the charge is carried along in the conducting material all the way to the load, where the load utilizes that electrical energy for whatever it needs, light energy, sound energy, whatever it is, right? Okay, then it says a battery goes flat when all of the stored chemical energy in the battery has been converted to electrical energy. The electrical energy is converted into other forms: heat, light, kinetic, and chemical. So basically, yes, inside of the battery, we have the chemical energy, which is then converted into electrical energy. When all of that energy inside of a battery has been used, that's when we say the battery is flat. Okay, the electrical energy is converted into other forms: heat, light, kinetic, and chemical. That is via the load. Okay, whatever is the need for electricity, whatever the electricity is utilized for, that's what the energy is then converted to. Okay. Okay, so the power source gives electrical energy to the charge. Some examples are generators, batteries, or photovoltaic cells. The load is a device which dissipates or uses the energy. Some examples are resistors, light bulbs, motors, speakers, chargers, so on and so forth. Okay, a torch is a simple example of a torch is an example of a simple circuit. The arrows indicate the flow of conventional current. We start off at the cell on the left-hand side, where the cell contains the chemical energy, which is then converted into electrical energy, right? We have the symbol for a single cell. The conductor takes energized load. Okay, one thing we can learn early on, this is our negative terminal. This is our positive terminal. Sorry, other way around. This is our positive terminal. This is our negative terminal. The bigger one is positive, the smaller one is negative, and electrons always move from. Could someone remind me? I totally forgot. Let me double check. Negative to positive. Positive to negative. Can I trust you? That's the real question. Is it possible for me to trust you? Yeah, it's bigger one to smaller one. That's how I remember it. So positive to negative, that should be correct. This is definitely correct. Okay. So the bigger terminal is the positive and the smaller one is the negative. Okay. But nevertheless, let's take away the main thing of the circuit. So it's always traveling from positive to negative. We'll go through it again later when we do proper circuits. But yes, we have the conductor, which takes the energized charge, okay, takes it to the load because the load needs that energy. Okay, so what is the load? In this case, the load here is the light bulb. Now, the light bulb takes that electrical energy traveling along the conductor and it converts it into light energy. Okay, it could be converted into sound energy, other chemical energy, anything that's required. Thereafter, the conductor returns the charge to the power source to get more energy. So basically the unenergized, I don't know if that's a word, but the unenergized charge goes back to the battery for more power and then continuously takes it to the light bulb, and the process continues and continues until the battery is flat. Okay, I hope that makes sense. Let's look at this just to note. Okay, EMF is the voltage measured across the terminals of a battery when no current is flowing through the battery. The switch is open. The EMF is the work done per unit charge by the source, right? So this definition is important. Okay, V terminal or potential difference is the voltage measured across the terminals of the battery when current is flowing through the battery. This is known as the operating voltage. Basically, what you need to know is that the operating voltage, like for example, if a battery is rated for like 12 volts, okay, it's technically speaking, okay, in your calculations for now, you don't really consider this, okay, but it's important, it's good to understand. If a battery, and if you go to Builder's Warehouse and you buy a battery that's rated for 12 volts, okay, it doesn't actually operate at 12 volts. Maybe it operates at like 9.5 volts. Okay, the reason as to why for now it's okay. You don't really need to understand that. So that's just it's telling us that this is EMF. Okay, and this is operating voltage. Okay, so in any case, for your calculations, you are generally going to be assuming that none of the volts are lost and you'll be using all the EMF. Okay, so you'll be using whether they say EMF or total volts of the battery, it doesn't matter for you guys. And for the sake of your calculation, you'll just be using the total amount. Okay, so yes, let's carry on. Okay, we're going to discuss Ohm's law, which I'm sure many of you know about. It's like a crucial part of the section. It's the pivoting part of the section, actually. It gets us into the calculations. So Ohm's law states, okay, so Ohm's law is actually a law that has a law, okay, and it also gives us a formula. Okay, so the law is that the potential difference across a conductor is directly proportional. So remember we said, what is potential difference? I don't think we said anything about it, but I'm telling you now that potential difference, okay, it's basically voltage. Okay, potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. Okay, so that's the law you need to by heart it. Okay, the formula that we get from Ohm's law is V is equal to I times R. Now, what is V? V is our voltage. The unit for voltage is volts, or V. V for volts. Okay, current, I is current. The unit for current is A for amps. R is resistance. The unit for resistance is omega. I think that's the omega symbol. And it stands for ohms. Okay. A volt on a circuit. Okay, we'll go through that a bit and we add it. Okay, so V is equal to I times R. We calculate voltage by multiplying it by the current and the resistance. We have voltage in volts, current in amps, and resistance in ohms. Okay, now when we talk about the relationship between current and resistance, it is an inverse proportion. I'm not sure if we discussed how do we express direct and indirect proportion. So direct, you will say A is directly proportional to B. If you want to say is that A and B are inversely proportional, you will say that A is directly proportional. This is what this sign represents, directly proportional to 1 over B. Okay, so you use the same symbol, but instead of saying B, you will say 1 over B. As soon as you say 1 over B, that means indirectly proportional. Okay, so now, okay, so this case here, we're saying that current is indirectly proportional to resistance, meaning when we increase current, we decrease resistance. Okay, so provided that voltage remains constant, just say the voltage is 50. If my current can possibly be 10 and my resistance could be 5. Okay, and I'm going to get 50, right? Now, again, voltage is constant. That's why I've got that little dot there. So what happens when I go ahead and I decrease my current and I make my current 2? What's going to happen, what's going to have to happen to resistance, it's going to increase to compensate in order to still get 50. It's going to have to become 25. So when I decrease my current, I will have to increase the resistance. So that's why those two are inversely proportional. Okay, we'll end like slightly late, like two or so minutes, right? 2 or 3 or 4 minutes, right? Let's talk about voltage. So voltage or potential difference, right? This is its defining formula. It's equal to W over Q. So it's the amount of energy delivered. So W is actually work per coulomb, work divided by charge. So we define it, when I say it's defining formula, it's the formula that gives us the definition. So voltage can be defined as the amount of energy delivered per coulomb. Amount of energy delivered per coulomb. Okay. Potential difference across the ends of the conductor is the energy transferred per unit electric charge that flows through it. That's just the definition again. Okay. Yes, its formula V is equal to W over Q. V is the potential difference. W is the work done or the energy transferred in joule. Please note that those are the same thing because these are terms that you guys will be dealing with a lot. Work done and energy transferred, and both are in joules, right? So the units are given. Let's do this. Work done, energy transferred are the same things. Okay, and Q is charge in coulombs, right? From like how we just learned in the previous section. Okay, so before we move on, let's go ahead and do a little calculation that utilizes the formula of potential difference. This is the wrong question. That's fine. All we have to do is, oops, magic. Okay, it says a battery transfers 60 kilojoules of energy to 5 kilocoulombs of electric charge. Calculate the voltage. Now remember, this is simple because voltage is equal to work done or energy transferred per coulomb. So firstly, this guy, let's move a bit down. This guy is in kilojoules. It needs to be in joules. So you multiply it by 1,000. So it becomes 60,000 joules. This guy is in kilojoules. It needs to be, sorry, kilocoulombs. It needs to be in coulombs. So you also multiply by 1,000. And you get 5,000 coulombs. This is equal to 60,000 divided by 5,000. 1, 2, 3, 1, 2, 3. 60 divided by 5 is 12, I believe. 12 voltages. Okay, so this is important to know as your basics, again, going into grade 11, going to grade 12, and of course for like yourself in grade 10, it's important, right, to know that this is the defining formula of voltage. And how do you calculate volts? You can calculate voltage utilizing this formula, even though most of the section we will be working with this formula, V is equal to I times R. It is important for you to know this as well. Okay, so let's call it there. Next time we will continue with current, resistant, and Ohm's law, series parallel. Please don't forget to do this question. The notes will be uploaded as soon as all of these lessons are done. Okay, so how do you have to convert? Yes, you have to convert. That's why the units are given here. you have to use, it's called SI units. Okay, SI units are the standard units of measurements that we use. In all formulas, okay, not all, but like I'll specify which ones you don't have to. But for now, you can assume that in this section, in all formulas, okay, you convert it to the SI unit. You have to know what the SI unit is for a particular variable or particular, what do you call these things? Like whatever you're working with, right? So voltage, current, like there's a specific unit you have to use. So if it's given in another unit, you convert it to that other unit. Okay, so let's call it there. It's a bit late. Before we do go, though, I do have a very important question for you guys. Who do you guys think is going to win between Manchester United and Liverpool? That's my important question for those of you who are soccer fans. Liverpool, obviously. Manchester United, of course. Okay, as long as I can see we have some potent fans. Yeah, okay, good to know. My grade 10 class is full of United fans. Okay, cool. Anyway, let's see. I don't know which team I support. You guys will have to guess. Okay, so let's call it there, guys. All the best. Have a good week at school. For those of you who are writing, good luck. Yeah, I'll see you guys next week where we'll continue with this, like I just said. And all the best. Okay, cool. Thank you guys so much. Jazakallah khair. Assalamu alaikum and goodbye.